Good morning, everyone. Welcome to this new research seminar at the IAC. Today we have a local speaker, Ignacio Martin-Navarro. He is currently a Ramón y Cajal Fellow here at the Institute. He finished his PhD under the supervision of Alejandro Batequis. And then he got a fellowship between Universidad de Santa Cruz in California and the Max Planck Institute in Heidelberg, right? Where he stayed for 4 years before returning home with a Ramón y Cajal Fellowship. So, well, you know the format of the talk. So,
thank you. Should I do something? No, I should. No, the chat was popping up, but it should be fine. So, oopsie. It feels. Let me put the clock on. It feels great to be giving this seminar finally after 2 years of being back home. Oopsie, of being back home, and my goal today is just to convince you that black holes are important in regulating the formation of an evolution of real galaxies, right? So to do so, I'll be summarizing some of the results we have put forward over the last 5 years or so. So some of them might be familiar to you, some of them not, and most of them are focused on studying the circulation properties of nearby galaxies. So when people try to justify the need for black hole feedback, you often see a figure like this. In this case, it's showing the star formation efficiency, so how many baryons you have, how many stars you have, the stellar to baryonic ratio as a function of halo mass, but you can have similar flavors of this. You can have this stellar to dark matter halo mass, or the ratio between the galaxy mass function and the dark matter halo function. But it's basically all of those ratios on the y-axis as a function of halo mass. They always have this sort of characteristic peak function where you have that galaxies are most efficient at forming stars at halo masses of 10 to the 12, and then as you go to more massive halos or you go to low mass halos, you get that you are less efficient in forming stars. You are less efficient in pulling gas into forming new stars. And the standard way of looking at it, or the actual way of looking at it, is that you have two feedback processes. So you have supernovae putting energy in low mass galaxies, expelling the gas away from the center of the galaxy, and reducing that way the amount of cooling and the amount of star formation. So it's, lower mass halos are less, the potential well is shallower, so a few supernovae are able to regulate. But then when you go to more massive halos, you become less efficient with supernovae. And then on the high mass end, you need this. We need this effect of black hole feedback. You can actually go and sort of simulate this. So this is a simulation of gas cooling in a massive halo. You have high redshift over here, and this is the specific star formation rate. So how many stars are you forming? How much cooling you have in your galaxy? And if you don't have black hole feedback, you end up you keep forming stars in your massive halo, and you end up with a massive galaxy that's going to be blue, as the one I'm showing up there. But that's not, real galaxies. Real massive galaxies, we know they are red, right? So you need to turn off the AGL feedback, and this figure shows here in black, to shut down star formation, to prevent further cooling, and to end up with a massive red galaxy, as you can see here. And this is traditionally called the overcooling problem. But I think there is sort of a marketing or a branding problem with calling this the overcooling problem, because this may seem as a problem with some sort of numerical artifact where you have some sort of numerical problem where you are forming too many stars. So when I talk to observers, and I think most of you people in the room about this are on the observational side, I'm going to take like a slightly different approach. So I'm going to go to this massive galaxy that was shown before. So this is the same galaxy as before, like a massive galaxy seen in the Sloan. And well, there it is, a massive red galaxy. And you have a lot of background galaxies and foreground stars in there. But among all these sources in there, there is is not like a foreground star, which is this guy up here. So this is a quasar. This is a quasar on the background of this massive galaxy. And these quasars, they have a very bright UV spectrum, right? So this is in particular, this is a spectrum from HST, from COS. And the light from this quasar is sort of going through the line of sight and it's reaching us, but it's passing through this galaxy. And actually, when you look at the spectrum, so if you look at this UV spectrum at the redshift of the host galaxy, you see that there is at the redshift of this galaxy down here, there is very clear absorptions in the spectrum of this quasar in the background, right? So this massive quiescent galaxy that we're looking at right now in there, that's only like the stellar component is only a very tiny fraction of the physical extension of the galaxy. So this actual galaxy, it's surrounded by a large, I mean, by a lot of material in there that we need to prevent, or galaxies need to prevent that gas from cooling and to forming new stars, right? So this is like from an empirical point of view, this is the overcooling problem. This is not a problem with simulations. So the overcooling problem is a problem that we have, that we need to prevent all this gas that is surrounding these massive galaxies. We need to prevent that gas to cool down and form new stars, right? So you can try to be a bit more specific about how much gas is contained. So this is a similar plot as the one before. So the star formation efficiencies. So this is the stellar mass divided by the expected value of fraction of mass in fractions that you have as a function of halo mass. And as you can see that you have at most 20% of your baryons in your halos are in form of stars, particularly massive halos, but around 80% of the baryons in your halos are not in the form of stars. And you need to prevent those baryons to cool down and to form new stars. Otherwise, galaxies, massive nearby galaxies, they wouldn't be ready, right? So this is the overcooling problem. The overcooling problem is not a problem with simulations. The overcooling problem is a problem that we have with the physics of galaxy formation in that way. So when you look at this and you see this sort of peak function, you're going to see this all over the place in galaxy evolution talks. Like you not to think about it as a problem in a numerical artifact, but that's a problem that we have that we need to address in order to really understand galaxy formation. So again, the overcooling problem is not a problem with the simulations. It's a problem that we have as a community. We need to understand this. We need to understand why all that hot gas is in there and it's not cooling down and forming new stars. And the thing, and all this business about black holes are the only source that we know that they are energetic enough to provide this extra source of energy in these halos, right? So it's not that we are going for this black hole field because because black holes are cool. It's because black holes are at least in massive halos, they are the only source energetic enough to actually regulate star formation and to prevent this cooling in massive halos, right? And something that'll come up during the talk is that all this business about quenching. So it's important to quench star formation. It's important to stop star formation, but it's very important also to maintain a galaxy quench, right? So it's easy. There are many ways of quenching momentarily a galaxy, but the tricky business is to keep those massive galaxies quenched. And that's something that still we need to understand. And a few of the results that I'm gonna be presenting today. Now the main problem with studying all this is that if you want to relate black hole activity or AGN activity to star formation, the two things change in time scales which are much different, right? So this is the figure before, and you see that the star formation changes in time scales of a few, say a giga year or a few hundred mega years. But the AGN activity changes. It's a very nonlinear process. So as soon as you put gas in the center of your galaxy, you are going to have your AGN turning on and off. So the AGN variability is much shorter than that. So it's hard to come up with a clean observational metric that is able to link two things that change in different time scales, right? It's like going in a highway and you are putting gas in your engine, and it's with the piston. It's hard to tell by the piston coming on and off if the car is accelerating or is decelerating, right? Because the time scales are so different. So here it's happening something similar to that. So this is a major limitation that people have, that we have when we're trying to understand all this process of relating quenching of star formation rate and black hole activity. So I said at the beginning that I'm going to be talking mostly about star population, detailed star population. That's what we have been doing for years. And I'm going to start with what might be probably the most famous or the most maybe important observational result from detailed star population analysis, which is nicely summarized in this figure. And this is very purely observational. So this is the equivalent width of one line. So you take your spectrum, you measure this feature over here, and you do it for many galaxies with different masses. So you have more massive galaxies here, galaxies with higher velocity dispersion. And you see that there is a nice correlation between the strength of this feature, this absorption feature, and the mass of your galaxy. Well, that's a relation we have many in astronomy, but the thing about this relation in particular, it encodes the three main characteristics of massive quiescent galaxies in particular, right? So this relation is basically explained by a combination of three ideas. So the first one is that when you go to more massive galaxies, more massive quiescent galaxies, more massive galaxies in general, they tend to be more metal rich, right? So that drives most of this correlation. Then on top of that, you have that when you go to more massive galaxies, you tend to have, these galaxies tend to be alpha enhanced. They tend to have an overabundance of alpha elements in there. And that's also like another factor contributing to this relation. And the final one is also when you go to more massive systems, you tend to have older galaxies. And this is kind of like a summary of many years of work on stellar population studies, is that massive galaxies become more metal rich, more enhanced in alpha elements, and older as you go to more massive systems. And the basic idea behind this is that, for example, this red here is like a cartoonish picture of the formation of one of these massive galaxies. So these galaxies form really old. So this is look-back time. So this is high redshift. So they form really old, and the star formation rate, or the star formation history was short, right? So you first pollute your medium with core collapse supernovae. These supernovae are reaching the produced iron, but they mostly produce magnesium or alpha elements in general. And then there was no time for supernovae type 1a to enrich the medium with iron, right? So if you have a very short star formation history, there is a lot of magnesium in here, there is little iron in here, and you end up with a old galaxy and high magnesium over iron, high alpha over iron ratio. However, if you have a more extended star formation history, like here, you produce a bit of magnesium here, but there is plenty of time for supernovae 1a to produce and to put iron in your galaxy. And therefore, after a few giga years of formation and evolution, you're going to have a galaxy that's going to be younger and with low magnesium over iron ratio. And this is kind of the picture that we have in mind when looking at these galaxies. So these galaxies over here, they have this high magnesium over iron and these old ages because they form fast and they form earlier. Actually, this is all to say because I got interested in this business of AGN feedback by this paper in 2016 by the Eagle collaboration, where they showed this ratio between alpha elements, this abundance of alpha elements, so this alpha over iron ratio as a function of stellar mass. And there's two observational results. So one from Ignacio de la Rosa there, who used to be here, he retired last year, and the other one from Daniel Thomas. But you see this relation that more massive galaxies tend to be enhancing in alpha elements. And what these people from Eagle said is that they needed to turn on the AGN feedback in their simulations to recover this enhanced magnesium over iron ratio in massive galaxies. So if they with no AGN feedback, so this red line over here, you get a flat relation. So the alpha over iron doesn't depend on galaxy mass. And this is not what we see. We see that more massive galaxies, we see that clear trend in there. And the idea behind this paper is really simple, and it's related to what I was showing before. So if you turn on the AGN in your galaxy, you are going to be in a case like this, where you are able to reduce the gas cooling, to reduce the efficiency of star formation. So your star formation history is going to be short. You're going to have like an old galaxy with a short formation time scale, and therefore it's going to have a high alpha over iron ratio. However, if you go to your simulation and you turn off your AGN feedback, you're going to have this continuous star formation rate over time. You're going to have a very extended star formation rate history, and you're going to end up with a low magnesium over iron ratio. So to me or to us at the time, this was great because this is something that we knew how to do, right? So we knew how to measure stellar masses, hopefully, and we knew how to measure magnesium over iron or alpha over iron ratios. So the only problem, or one of the main problems, is that in the simulations they were able to turn off the AGN, that's something we cannot do in real galaxies. So we needed to come up with something slightly different. So this is going to be sort of central to during the rest of the talk, but we know that black hole masses, so more massive black holes are in the center of more massive galaxies. So this is basically what this relation is telling you. And what we did was, okay, let's assume that at fixed stellar mass galaxies are the same. So we're going to use the scattering this relation in our favor, right? So we fix the stellar mass or the velocity expression. And since the energy that a black hole, so the energy that a black hole radiates scales with the mass of the black hole. Basically, you know, that a black hole grows, that the energy is released, and so the more massive your black hole is, the more energy that the black hole has released over time. So we use the scattering this relation to empirically modify the amount of energy that black holes are putting in galaxies. So in a way, we were expecting that what we call here undermassive black hole galaxies are galaxies below this same sigma relation. So those are galaxies with lighter black holes. Those are galaxies in principle with where the black hole has, through all this life, has put fewer or less energy in the galaxy. And on the contrary, if you go to these overmassive black hole galaxies, those are galaxies that probably have experienced a lot of a very intense effect from this black hole. So we did that, and then we calculated the stellar population properties, and we found something that was fairly consistent with the idea that was presented before. So the red and blue is the meaning before. So red points in here are galaxies with more massive black holes, these overmassive black hole galaxies, where we expect the black hole feedback to be more intense. And indeed, you can see that at fixed velocity expression, galaxies with more massive black holes, galaxies with a lot of AGN feedback in the past, tend to be older. You know, they formed before, they stopped forming stars before, and they are also more enhanced in alpha elements. So this was a first indication that that black hole, the activity of a black hole during its life was sort of imprinted on the stellar population properties of our galaxy by doing this trick of playing with the scattering in our favor. So we were fairly happy at that time. But we could do a bit more, right? So we have we can measure indices. So this is based on looking at particular features in the spectra of galaxies. But you can do a bit more since we have great models here in the house. So Alejandro has been doing this for many years, and he has reached to a level where, as you can see, the data in here is the black, and the best fitting model is in red. So this is the optical spectrum of well, normal galaxy. As you can see, the models are really able to capture what is behind in the data with a very, very tiny error. And what we're doing here is basically recovering the star formation history of a galaxy. So we are combining different models with different ages and different metallicities. We are combining them in a linear way to match the spectra. And in that way, we're able to recover how much mass this galaxy form as a function of time. So we are basically recovering the evolution of star formation rate as a function of look-back time. So we did that for this very same sample. For this sample over here, we had optical spectra for all of them, and we recovered this. So this is a similar exercise as I was showing before. So in red, this is the line of the evolution of the star formation rate as a function of look-back time. So here redshift 0, and here's high redshift. And in red are galaxies with more massive black holes, with more energy put in by the black hole. And as you can see, they quench faster, so they start forming stars rapidly, but they got quenched really fast. And also they are not really able to form new stars here at redshift 0. However, if you go to this undermassive black hole galaxies on the blue, on the bottom part of the MC relation, where we expect the black hole feedback to be cumulative, less important. It seems that the star formation histories are more extended, and they are more able to form new stars at redshift 0. And this is actually, you can more clearly see in this sort of cumulative way. So this is how much mass they are formed as a function of look-back time, and the vertical lines indicate where these galaxies form, these stacked galaxies form 90% of their mass. And as you can see, when you have a more massive black hole, something over here. When you have a more massive black hole, your star formation histories tend to be shorter. You tend to quench more efficiently your star formation, and that's why you end up with older ages and higher alpha beta ratio. So we were pretty happy at that time, and the idea that we have is that that this energy that black holes are continuously putting in the halos are able to just keep hot the gas around your galaxy, right? So the key thing about this overcooling problem is prevent this cooling. So the idea is that you are able somehow to increase the entropy to sustain a very hot corona around your galaxy. So we actually try to look for this, and so for some of these galaxies there was also X-ray measurements of the temperature of the gas around the halos. So here, this is what I'm showing. So this is the temperature of the X-ray corona as a function of stellar velocity expression. Those lines are the virialized lines. So assuming that the gas in your halo is virialized. So first of all, you see that all our galaxies are of the virial expectation. This is normal because you have additional sources of energy in there, like black holes, for example. But on top of that, you see that when you have these overmassive black hole galaxies, where we have these galaxies where we think that the AGN feedback was more important during the evolution of these galaxies, those galaxies over there at fixed velocity expression, which should be the main parameter driving this, those galaxies tend to also sustain hotter coronas in there, right? So there is this indication again that we see not only on the stellar population properties, but we also see that the coronas, the gaseous coronas of these massive galaxies, when you have a more massive black hole in there, the gas around the galaxies tend to be hotter as well, which again goes in line to support this idea of black holes putting energy in your galaxy and preventing this further cooling, not only quenching your star formation, but keeping these galaxies quenched. So from the almost megaparsec scales of the corona to the center of the galaxy. The picture seems to be fairly consistent, that telling you that the cumulative energy put by black holes is what seems to be a main driver of one of the key ingredients in shaping the stellar population problem. Now, let me see. This is going to be tricky. Videos in presentations. Oh, it works. There you go. This is the problem with time scales. This is something that I think the community working on this business is something that still fighting, because maybe the older people in the room may remember this early simulation of AGN feedback, that the ones that became very famous, where you have the merger of two spiral-like galaxies, and then you are going to have this burst of, well, now it's a bit slow, but sort of working. So you have this idea of two spiral galaxies with a black hole in the center merging together and fueling the black hole. And as you can see, at some point the black hole just grows and expels away all the gas from the center of the galaxy. And I think in our community, somehow in galaxies in general, the idea that sort of crystallizes that black holes regulate star formation mostly in this violent way, kind of quasar-like approach, where you just get rid of all the gas in your galaxy, and you end up with, after the merger, with a tiny sort of all thing in there where there is no more gas because the black holes just put all that gas away. But as I was showing before, now more newer simulation, and also from the observational point of view, it seems to be that it's not only this phase that is able to expel the gas from the center of the galaxy. So this phase is important, but there seems to be a probably even more important phase where it's the cumulative effect of a black hole, where it's actually quenching and keeping quenched again star formation, right? So these bursts of star formation of nuclear activity, they are important, but this is probably not the right picture when we try to really understand the quenching of galaxies through all their history. So we wanted to explore this a bit more. So we selected a sample of nearby, a few thousand nearby active galaxies. So the selection function was a bit weird because we wanted to do something slightly different at the beginning. But in the end, when we ended up with a few thousand sources with halo mass estimated, so we knew the mass of the halo where they were living at. We knew that they were active, so these were active black holes. They were classified as AGN, and they have optical spectra, right? So this is an example of one of them. Dealing with this is a bit trickier because, well, you can see the spectra, or this spectrum in particular, is not as clean as before, but we were able to sort of at least as first order, get a clean-ish stellar continuum, and we play the game, and the same game as I was showing before, trying to recover the star formation histories of these guys, right? So we have the star formation history, the evolution of star formation rate as function of loopback time for a few thousand objects, and this is kind of the main result of this paper. So you have again star formation rate, specific star formation rate as a function of, so this is star formation rate divided by the stellar mass at that time as a function of loopback time. Again, redshift 0, high redshift here. The orange line is a control sample, so it's a sample with the same stellar mass as the blue line, but with no AGNs, optically selected AGNs in there. And the blue line is our sample of active galaxies. So here you can see that the AGN, or the sample of AGN, they experience this what people call rejuvenation. So this recent burst of star formation that we think it's fueling the current episode of nuclear activity. So in these galaxies, there was gas falling into the center of the galaxy. So that creates new stars, and also that lights up the AGN. But as you can see, these galaxies that we now see as nuclearly active, the quenching process of these galaxies started way beyond now, right? So it's not that the nuclear activity that we are seeing right now is actually driving the current quenching of star formation. So this galaxy has been on their quenching path for many giga-years now, and what we see, or what we think we're seeing now, is just another episode of nuclear activity. So you put gas in your galaxy, that grows a black hole. That black hole puts more energy into your galaxy, and in the end, it's not really like this burst of star formation what quenches the galaxy, but many of these episodes as a function of loopback time. So those are what we think are feeding the black hole and putting energy and quenching the star formation. So you only see these episodes here at redshift 0, but that's because the resolution, so the time resolution, it's much coarser here. So we are in practice, where even if these bursts are happening probably through all the life of a galaxy, we can just not see them. This is a limitation that we have with this technique that we're using, right? But this is, the fact that we only see that burst there doesn't mean that it's not happening, and it's probably happening as you go back in time. But again, the main idea that I think from this figure is that current AGN activity is not related with the overall quenching of this galaxy. And something that I found particularly interesting at that time is that the mass of the halo so we selected the control sample was selected to have the same stellar mass. But then when we look at the halo masses estimated through abundance matching, the halo masses of AGN galaxies were slightly different than the halo masses of our control sample. So if you plot the same ratio that I was showing at the beginning of the talk, so the ratio between stellar and dark matter halo mass, you remember this U form, and you see that in a way the halo masses somehow, or stellar population properties, the age of your population or the age of your galaxy somehow seems to be sensitive to the mass of the host halo. Maybe and the idea that we have is that maybe these AGNs that we are seeing right now at sort of an early stage of evolution, that we are seeing that if we let them evolve, they are going to end up being like a normal galaxy, and we just see them active because they are younger and there's more gas in there able to fuel star formation. And this was a very short, but now Laura is a student working with Jesus and myself, and she's doing a great job. She's taking this way farther than we initially thought, and she's actually going and exploring this in much more detail. So this is a paper that she published early this year, where she's color coding the stellar to halo mass relation with the stellar population properties, and stellar population properties seems to care about the halo masses, and not only the mean age, mean metallicity, and mean abundance pattern, but this is a paper that she's about to submit, and she's also showing that the star formation history, not only obviously the integrated quantities, but when you look at the evolution of those galaxies, the evolution of star formation rate over time seems to be sensitive to the mass of the halo, in particular for low mass halo. For very massive halo, everything is very old, and it's hard to tell if there is any difference in there. So stay tuned, because this is going to come up hopefully soon. And now I'll jump back to this black hole business, and I'm gonna go to two limits. So I'm gonna go to low mass galaxies on one side, and then go to very massive halos at the end of the talk. So this is a paper that we did with Mar Mezcua, who's now in Barcelona, and so we wanted to see if this idea that we saw at the beginning, where the separation properties of massive galaxies, where we saw that they depended on the mass of the black hole, and the idea when we started this is that because of the plot that I showed at the beginning, if you go to low mass galaxies, black holes are probably not that important, and supernovae feedback starts to become the main source of feedback, the main source regulating the baryonic cooling in low mass halos. So there is labels missing, but this is the black hole mass calculated through this single epoch spectroscopy. So depending on, so these are active galaxies again that we use the width and the luminosity of the lines to constrain the black hole mass. But again, so a proxy for black hole mass as a function of velocity dispersion, and we played the same game. So we divided our sample in low mass, so that you can see these are low mass galaxies, and we play the same game with redder points being these overmassive black hole galaxies, and in blue these undermassive black hole galaxies. This is kind of the approach. Things were looking better than the broad lines and the very star-forming guys that I showed before. So this is the typical spectrum of one of these dwarf active galaxy, and again the Sloan spectra in gray, and the data in black, and our best fitting model in red. As you can see, again, we are doing a fairly good job at fitting the data. We have this measurement from black hole masses, the errors, the uncertainty, the systematic errors in black hole masses here are larger. So that's an important caveat in our analysis. But we did the same, and in this case, when we moved to lower mass systems, this difference that we were finding before in more massive galaxies, it wasn't there in these low mass galaxies. So somehow this dependence on black hole mass that we saw in the high mass end sort of disappear when you go to this, and it would sort of make sense in this scheme where low mass galaxies are more supernova driven than higher mass systems that are more black hole driven, right? So you can actually combine the two results. So we took all measurements for the ones that we use for the high mass end, and we combine them with the measurements of the low mass end, and this is basically the same figure as before. But you know, when you go to massive galaxies, when you go to galaxies above the mass of the Milky Way, basically you get that the star formation histories of your galaxies do depend on the mass of the black hole in the center of your galaxy. But then when you go to low mass systems, you lose this dependence, and this is in agreement with this idea of a transition between a supernovae driven regime down here in lower mass halos towards an AGN driven regime at higher mass halos. And something also interesting that we were not expecting either is that as you see, there seems to be a flattening in this relation between black hole mass and sigma. So the red line is a compilation that Renko van den Bosch did in 2016, and our relation in this paper is the blue line. And when you plot all of them together, they cross at the sigma or at the galaxy mass. That is actually this transition mass that where this transition between supernovae and black hole feedback regimes seems to happen. So this plot sort of summarizes the main idea of, you know, low mass galaxies being more supernova driven and high mass galaxies being more black hole driven. There's important caveats with this analysis in particular. There is the non-stellar emission from the active black holes. That's a pain to deal with in this low mass system where there is this emission from the black hole, and also that there is strong systematics in the mass of the black hole. So it might be that part of the signal, that there might be some signal, some dependence on black hole mass, but we are missing that signal just because we're shuffling our galaxy because we are not able to really measure with precision our black hole mass measurement. But in any case, this picture seems to be consistent with what we had in mind. And I'm going to finish with our most recent paper on this. That actually started in while I was still in RMPIA, and Annalisa Pilepich, she's the PI of TNG50, one of these state-of-the-art numerical simulations, and she was giving a seminar in their RMPIA, and she was showing this video from TNG50, where you have simulations. They are nice, and they have all these outflows. Some of them might be real, some of them may not, but you get all this fancy thing going on, and oops, a bit fast. Yeah, so you have all these things going on, and so galaxies, when you look at them in real time, they are much more active than we think they are. So now I want you to pay attention, because this is what caught my eye when she was giving the talk, to one galaxy that is going to appear on your right. So it's going to be a disk appearing on, as you see, and there is this huge outflows coming from the center. Now I'll say here from this disk, right? So this is our guy. So this is in the simulation. There was this disk-like galaxy kind of moving this direction, and then gas was falling into the center of the galaxy, filling the black hole, and the black hole was putting away all this material through these huge outflows. And so when I first saw this, it was like, oh wow, if you are a satellite galaxy, if you're a galaxy around this galaxy with a massive black hole, it's called galaxy A. My idea, or the thing that we wanted to test it, was that probably the life of the galaxy is going to be much more complicated than the galaxy, like a galaxy B, which is sort of shielded from the feedback from the central supermassive black hole, right? So it's not the same that if you are like a low mass satellite orbiting freely around a galaxy, and you get all this outflows from the black holes, but if you are a galaxy B, you're going to be orbiting, doing your stuff there, but you're not probably going to be that much affected by the activity of the black hole. So we set out to do a very simple experiment. So we went to Sloan. We took all the centrals that we could find. So there are a few thousand of them, and we aligned all of them together. So we used the pipeline of Sloan to calculate the minor axis. So we put all of the galaxies in the same sort of orientation to construct like a huge meta galaxy, and we did the same with the satellites, right? So we rotate the central, and then we look at how satellites were distributed around this central galaxy. And the experiment that we did was simple. So this is, it's simple, but it might be not so simple to explain. So this is the orientation of the galaxy. So 0 means along the major axis. So people in this might be tricky, but you have like you have your satellite galaxies on the plane of the disk, and then like 90 degrees will be along the minor axis, and then 180 is kind of on the other side of your disk-like galaxy, and so on and so forth, right? So the minor axis is in yellow, and the major axis is one there and 180. And we look at the quiescent fraction. So we took all the satellites, and we look at how many quiescent, the star formation in the satellites around the center, how many quiescent galaxies you had in there. And my expectation when we did this was, since there was this outflows of gas, we were expecting that those galaxies along the minor axis, those satellites along the minor axis, so those facing the southward from the central black holes, they were going to be very affected by the feedback from the central galaxy. And those were the ones that I was expecting to have a higher fraction of quiescent galaxies. We thought the star formation was going to be lower in those satellites really facing the outflow, right? So I was expecting something that the quiescent fraction was actually going up, maximum in the minor axis and the other. But we actually found the opposite, which was interesting. So we found that a massive galaxy, massive galaxy. So along the minor axis, so these galaxies, satellite galaxies facing directly the outflows from the central black holes, those were more star forming, or they were more star forming of them. So the satellites in there, for them was easier to keep forming stars, which was surprising. It's also nice because usually in the kind of stuff that I do, I get mostly like linear relation. It was nice to, for once, having something that doesn't look linear. And you can do something also a bit trickier. So you can look at what we defined as a an isoquiescent fraction. So look at the distance at a given angle, look how far or how close to the center of your galaxy you have to be to recover the same fraction of quiescent galaxy, and we recover this very anisotropic distribution, right? So if there was nothing going on in there, you would expect that everything is symmetric, and you would expect like some sort of a circle sphere like here, but as you can see, this has nothing to do with that. So it's if you are along the minor axis, you really need to go close to the center. So it's really hard for galaxies. It's really easy for galaxies along the minor axis to keep forming stars, which was surprising. This trend and this signal seems to have some sort of interesting correlation. So the strength of the signal is stronger for more massive galaxies. So if you have a more massive galaxy, the signal is stronger. It actually goes around for satellites. So the signal is stronger for lighter satellites. So if you have a low mass satellite or lower mass satellites suffer more from whatever it's going on behind it. And something also interesting that was again suggesting the idea of black holes being behind this is that we play the same game as before of separating overmassive and undermassive black hole galaxies. So if you have an overmassive central, your signal is strong. So if you have a more massive black hole in the center of your galaxy, your signal is going to be stronger. And if you have a lighter black hole in the center of your galaxy, of your group or your cluster, the strength of the signal is going to be weaker. So this was suggesting that black holes had something to do with this. Since I was at MPIA and there was Analisa was there, so we went to natural wave was to go into Illustris, so we went to Illustris PNG. And in the simulation, similar signal emerges. So the in green is what we recover in TNG. This is not trivial because in the simulations, the feedback, at least effectively, is isotropic. So there is no like a preferred direction in the way of injecting energy in your galaxy. So this is something that in simulations were not tuned for to reproduce. But again, we weren't sure. I mean, the signal was there. We tried to run the simulation with no black holes in there because that's something that they can do. But they only had that for like a low volume, so we could not. We didn't have enough galaxies. So what we did something slightly different. So we went to the previous generation, so not to TNG, the last generation, but to the previous generation of simulation, which is Illustris. And in Illustris, the AGN feedback was less efficient. So basically the cosmology is the same, but the implementation, one of the main differences is that the implementation of AGN feedback is completely different. In TNG, it's much more efficient. And in this case, suggesting again that black holes have something to do with this. In Illustris, in the sort of same cosmology, but different black hole feedback implementation, weaker black hole feedback implementation, actually you get a flatter, a weaker signal. Again, suggesting that the black holes were behind what we were seeing. And something that obviously we cannot do in observations, but people doing simulations, they can do. In TNG, they know that what quenches star formation in their case is the amount of kinetic energy that you put in your galaxy at the end of their life. And when we look at galaxies with that have released more kinetic energy, you see that the signal is stronger. So that's in red. And where we look at this under kinetic energy galaxies, the signal is weaker. So at least in this simulation, the signal seems to be highly related to the activity of the black hole. So the idea that we have in mind, or the explanation that we have for the signal that we're seeing in Sloan is that AGN feedback. So yes, you have these outflows going away from the center of the galaxy. They are escaping through the minor axis because that's the path of less resistance. But what's happening in the end after the evolution of a galaxy is that these outflows end up carving low density bubbles along the minor axis. And in the end, what we think is going on is that the environment, so ramp pressure stripping is going to be much less efficient here. Although you have these outflows of high velocity, since the densities are much lower, galaxies orbiting along or passing through the minor axis are going to be much less affected because yes, there is fewer gas in there. So for them, it's easier. Although they see these outflows and there is maybe one particle going super fast, but they are not as affected by the cluster environment. But if you are along the minor axis, there is a lot of gas in there, so you really feel the effect of the environment through ramp pressure stripping. And this is a figure. This is a contrast density contrast and in the simulation, as you can see, the density is actually lower in the gas perpendicular to the minor axis and goes towards the center, as we are seeing with this iso distribution. And you can play this final game of, you can look at the relative gas over density, so you can do what we did with Sloan, so look at the over density as a function of position angle, and you get this obviously peak function that really looks like what we are seeing in the optical in the real galaxy, right? So what we think is that these galaxies living in relatively lower densities, the quiescent fraction is lower just because these satellites are more able to, are less sensitive to the effect of the environment around them. And that's basically it. So this is my summary. Something that it's not really coming from our results, but something that I want you to keep in mind is that black hole feedback, we need that. So the problem with black hole feedback is not a problem with simulator, it's a problem with us as a community. That is important to quench galaxy formation, but to keep those galaxies quenched is also very important. Our observational results telling us that, you know, when you have a more massive black hole, you tend to have in your galaxy, you tend to have older stellar populations, you tend to have more alpha enhanced populations, you tend to have hotter X-ray halos. So all of that suggesting that the cumulative energy that black holes are putting in your galaxy is kind of driving the quenching. And this idea of cumulative quenching, of a delay quenching, in the sense that it's not really the energy that black holes are putting now in your galaxy what's creating this kind of long-term effects on galaxy evolution, but it's more the cumulative effect. So many of these episodes putting more energy, heating up the gas around your galaxy, keeping those galaxies quenched. What we think is driving really gas cooling in these massive halos. When you go to low mass halos, things get weaker, but there's still a lot of work to do. And Anna, Mara, they are working on that, trying to look for signatures of AGN feedback or effects of AGN feedback on lower mass satellites. And again, this idea that Laura is now pushing forward that halo masses may play an important role in regulating the baryonic cooling, and in particular the extrapolation properties of nearby galaxies. And the final one, as a summary of what I was showing before, is that the effect of black hole feedback, the black holes have an impact on the central of the galaxy, but they also can have an impact on much larger scales, like even megaparsecs. As you saw, the signal was reaching up to the VR radius of these halos, and this may be a way of introducing some conformity. Some of these observations that, you know, the properties of central galaxies seem to be somehow coupled to the properties of satellites, and this may be a way of helping in linking the properties, because you have these outflows going extending way away from the center of the galaxy. Yeah, that was one. Thank you.
Thank you, Nacho. So now it's time for questions. First questions here in the aula.
Thank you, Carl. Thank you, Nacho, for the nice talk and for putting together all this comprehensive view of the work that you have done, the evolution of Martin-Navarro's publications. And so, if you go back to the plot of the rejuvenation.
Mm-hmm. Wanna do like this?
So
yeah. Sorry. Yeah,
okay. So does it mean that so the star formation history have been different, no, in your AGN sample as compared to the control sample, mm-hmm, in a way? So would that imply that some galaxies are different? I mean, the galaxies that today we see as AGN, mm-hmm, have been different in the past than the ones in the control, because that would be against the idea of the on and off.
Yeah.
And also what you said at the beginning, that triggering an AGN is an easy thing, no? Which I no, you know, but
yeah,
it could go against this on and off thing, no?
Yeah. So the star formation histories are deep. I don't have that figure here. So the star formation histories are different if you only match in star mass. So once we match in stellar and halo mass, the star formation histories were the same. If there was no rejuvenation, but this rejuvenation in mass, it doesn't matter. So the mass of the galaxy, the growth of the mass, this in mass doesn't count. So when you look at the star formation histories, if you only select in stellar mass, they are different. If you select in stellar mass, if you match in stellar and halo masses, our idea is that once you match in stellar and halo masses, galaxies with or without a gen are the same. It just happened that the ones at the end have a recent episode of gas cooling, and that's it. An interpretation. But yeah, the star formation history in this case are different just because the halo mass was different.
Hi, Ignacio. Thank you for the nice talk. When you show your results on the overmassive black holes and low massive black holes, I guess that you are using SLAM data also for this?
For this one?
Yes.
No, this is data from sort of a blind survey that Renko did. So this is long slit data from long slit optical data.
But you are using a central aperture or something like this
This
to
is
get this.
calculated in 1/8 of the effective radius of the galaxy. So it's a fixed aperture in terms of effective.
Okay, my question is about this. It's about aperture and how you can extrapolate the result that you're getting in different in your different works, taking into account only the central part of the galaxy or taking the whole galaxy as I mean in the measurement of your stellar population.
Yeah.
I mean, how do you think it can affect also, for example, to our views of inside-out formation for the galaxies and this?
Yeah, I don't think. I mean, personally, or we haven't done any specially result analysis so far. We wanted to, but in this case, so for the other one, it's long data, and you're with a fiber, and that's it. In this case, we had long slit data, but the problem is, since this was a blind service, that the slit was put like randomly over the central galaxy. So I had to stick to the relative central part of the galaxy because that was the only one consistently probed by the long slit. So ideally, something that we could do if we had a long slit along the major axis, for example, was to look at the gradients in the population properties depending on the mass of the central galaxy. But this is something we haven't.
I few surveys like manga or things like that.
Yeah, but yes, the problem is that there vacuum mass direct vacuum mass measurements, there are only a few of them, like 100 galaxies where we know this. So in manga, I don't think there are none of them because manga is farther away. But the idea is, I mean, that this is something Laura put in a proposal to do this, but bad weather. So, but this is something to be done in the future.
Any other question here?
Ignacio, thanks for the nice talk. Maybe I missed it, you said it, but if I understand well, an assumption, a strong assumption, underlying one, to obtain these results is that there is a very tight relation between the velocity dispersion and the stellar mass of a galaxy. And then the only factor that could imply a deviation from this relation is the mass of the black hole. So how strong is this assumption? Are there other mechanisms that could shift in one direction or the other?
It's just a strong assumption. There is yeah, that's been bothering me for a while. So yeah, there is other assumption. So environment might play a role. There is some indications that the environment may affect the slope and normalization of the MC relation, but it's not clear. The problem with the MC relation is that we have so few objects that it's hard to come up with secondary trends in there. So we don't really know. So we went actually to the M sigma because it's more stable than the black hole mass, mass, for example, that we know that depends on some of the stuff. So that's why we went for sigma. But yeah, there could be some other sources. There could even be some sort of evolutionary history where these guys were here. There was no time for them to grow the black hole, and they are going to end up like they are younger versions of the galaxies above. We have tried to look at this in simulations, but the problem with simulations, at least with the one that I've looked at, is that these relations are too tight. The effect of the black hole is so strong, I think, or the way that simulations are implemented in AG and feedback is so strong that, for example, if you look in TNG, I mean, it's not that I'm saying that they are doing this wrong, but you know, when you look at, for example, the relation between black hole mass and halo mass, it's like pretty much like a straight line. There's no scatter. So we cannot really play this game, and we cannot understand the scatter because there is no scatter in there. But yeah, there is visible. There could be some other stuff going on.
Connecting to this last question from Giuseppina, from an external ignorant about this thing, how do you find this sigma? The sigma is there. Oh, sorry. Let me just. The sigma? How do you define this sigma? Is this the RMS of the galaxies within the halo, or the
since we have long speed data, so this is the velocity expression. Yeah, this takes also into account this blindly the rotation velocity of this. So it's the velocity expression in the center of the galaxy, velocity expression measuring
From the lines, measure from the lines spectroscopically, or how do you measure?
by fitting the spectra. Yeah. But this, since we don't have resolved spectra, this takes into account both the rotation of the velocity. The rotation is not super important because this is in kind of 1/8 of the effective radius, but
A question regarding to this enzyme relation that you show for the low mass extent. So first, I wonder about your classification or division between overmassive and undermassive. I mean, when you see this kind of plot or this kind of relation, usually they are classified by the by the galaxy morphology of the agent type or batch type. Yes. Yes. So this is one not clear for me. How are you considering this overmassive and undermassive? Only you take into account the linear regression? For this?
Yeah. For this,
Okay.
so there might be some other effects in here. This one in particular, this is tricky. That's what this result is. It's there, but it's a bit weaker. Here, black hole mass estimates are also coming from broad lines, so the error it's larger. But we didn't split into different types. It's true that in the very low mass end you don't have many early types, so this is the morphology that are more under control. And in the high mass end it's the same by a selection function. So to do your dynamical modeling, you need to go to galaxies where the light profile is smooth. So by construction, in a way, you're also selecting early type galaxies. So we don't have that much of a mix of morphologies in here, but that might play a role. And,
okay, and the other one also, I think in the next slide when you show the other enzyme relation. This one, you mentioned about the flattening in the low mass end. So this is interesting because when you have this also relation, it's common to see the flattening in the opposite extent. So when you have the higher massive black hole, so what could be this related to the flattening that you're showing?
you mean the flattening in the very high mass end?
No, in the low mass end. I mean I'm used to see the flattening in the high mass end, but now you have this flattening in the low mass end.
Yeah, so this flattening we didn't want to put. So this we are not the first time, the first seeing this flattening. It could be a real flattening because the effect of AGN feedback is, or black hole feedback is different in there. But there is also strong selection biases going on in there. So it's not super clear where this is like a true flattening or it's like an artifact. But it might be that it might be real. It might be related to how black holes are releasing, or how the mass of the black hole is related to the mass of the galaxy, but we don't know, and we don't know how to know.
Related to this again, and I'll pass Mike to you after that. I kind of skeptical with this last figure you're showing here on the low mass end. So I'm a bit surprised that naively we have thought that for smaller galaxies, black holes would still have the power to actually impact the star formation history in this kind of halos. And you say that in this kind of masses, low masses, it is the supernova actually driving the driving force there. Has anyone computed the energetics of black holes in such small halos?
So there is work now working in that direction, but this has to with what Cristina was saying. Maybe it's not that easy to feed a black hole in particular. What people think is going on in these low mass satellites is that as soon as you have so there's gas falling towards the center of your galaxy, you're going to have star formation and you're going to have supernovae. Supernovae are going to be able to really regulate, to prevent gas for farthing falling into the center of the galaxy. So these guys have relatively low mass black holes in the low mass end just because supernovae are preventing the gas for reaching the center of the galaxy. So it's not that black holes it's not an energetic balance. So if you are able to feed your black hole, you're going to basically destroy your galaxy. But the things that supernovae are preventing this gas from really falling in and feeding the black hole.
So just not so super fast observation. When you said that you find in simulations a very tight relation, that is in TNG, because when they do the seeding of the black hole, they put it on basically on the Magorian relation. So usually the black hole is already kind of massive, stays there and does what it does. I mean, it flickers, it's got accretion, etc. While in other simulations, they just see that 10⁵ black hole stays there and it does whatever it wants.
Yeah, so I haven't looked into Eagle, for example. I don't know how it looks. But
so yeah, in Eagle we have got like much more scatter on that. We show it in a paper that I did with James and Topo. So if you want, can look.
In the Zoom chat, there is a question by Mark Balcells. You can read it from there. Could it be the other way around? So the matter distribution around a galaxy, which is strongly isotropic due to the cosmic web, determines the direction of the minor axis,
Yes.
and therefore the axis.
So yeah, that's the other alternative that we were exploring. We don't support that scenario because, well, first of all, because the relations that we see between the strength of the signal and the mass of the satellite, the mass of the central, and in particular the mass of the overmassiveness of the central galaxy, and also because the comparison with Illustris was made to actually address this point, since the cosmology in Illustris is very similar to the cosmology in TNG. We were expecting that changes in the signal are not driven by a sort of large scale behavior, but the behavior of the main change in between TNG and Illustris, which is apart from other stuff, the implementation of agents with that. So the strongest argument that we have, at least from the simulation, is that the TNG and Ignacio, the main difference is that it's on the agent feedback implementation, and there is a difference in the signal.
Okay, any other question from the room? Otherwise, let me quickly check the YouTube channel. But for that, I might need you to actually stop sharing. Do you mind stop sharing?